Hello, and welcome to another Sesam video by DMVGL Software. In this video, I will show you a brief overview of how to design your subsea equipment in Sesam. In this case, it's a subsea manifold. We start here in Sesam Manager. Sesam Manager is where you'd set up your project. It's nice and easy to follow, and details step by step what your design scenarios are for your project. So here I start with an in-place lift and transportation model in Genie, the purpose of which is to get structural code checks on my beam elements. Then I convert that model from beam elements into shell elements to get a finite element mesh automatically generated by Genie on the entire structure, the purpose of which is to go in and look at hotspots on my structure and do more detailed local detail analysis. I then do a simulated lift through the splash zone using Sesam to get my sling loads to get a more accurate, less conservative dynamic amplification factor. Finally, I do nonlinear design, do ROV impact, dropped object analysis, and installation analysis using a nonlinear solver. And this is one of the great strengths of Sesam, and why I truly believe it's a total solution when you're designing subsea equipment, is I can go from structural code checks into finite element mesh, into a simulated lift through the splash zone, into nonlinear analysis, all using the same software and without having to resort to any other software. And the beauty of Sesam Manager is that it facilitates the communication between all these modules inside Sesam. So I don't have to do any file manipulations in the background or do any file management. This is all done by Sesam Manager. And if you set everything correct on the right side here, you should be able to right click and run. So without further ado, we start with the in-place lift and transportation, and I'll see you in Genie. Hi, and welcome back. So now we're inside Genie. This is the in-place lift and the transportation model. The purpose of this model is to do structural code checking on my members to get unity ratios. And one of the advantages of using Sesam is I can have my in-place, my lift, and the transportation under one file in one model. I don't need 3 separate files to represent each case. What that means is that if I change a member for the in-place, for example, I don't need to go into the lift file and update that member and the transportation file and update that member. This greatly reduces human error. And the way to set that up is under activities. You would have an in-place, a lifting, and a transportation activity. And the way to tell it which members belong to which activity and which boundary conditions belong to which activity, that is done using sets. So under sets, under the in-place set, I told the program that all in red is included in the in-place activity, so I included the soil boundary condition, but I did not include the slings and the sling boundary condition, and vice versa for the lift set, so I included the slings and the sling boundary condition, but not the soil boundary conditions. And the way to create a set is by selecting your members that you want to include, go to named set. Here you can either define a new one or pick from an existing one. And then what's left is to right click your activity, going to activity monitor, going to meshing, edit activity, and here under mesh subset you pick which set you want to include in that activity. And then after defining your load cases and your load combination, you're ready to run it. So all you have to do next is just start the run. It will run. I've already done that. Next step is going to be to create a capacity run for that activity. This is where the structural code checking is done. So for the capacity lift, this is based on the lifting analysis, and I've already created one for the in-place and for the transportation. So if I right click and make this one active, we can see This is the capacity members that I've created, and this is my capacity run for my lift. So here is where I can list my members based on which ones are more the more critical members. So I can color code these, for example. So as you can see here, and I can also label, and that's the way to do it for the other three cases. Next step was going to be to convert the beam elements into shell elements to create a finite element mesh so we can visually check for any hotspots on the entire structure. So I'll see you in the finite element mesh model. Hi, so now we're inside the finite element model. This is the same structure that we saw earlier. The only difference is I changed all the beam elements into shell elements so we can get a finite element mesh of the entire structure. The purpose of this model was to visually check for any hotspots on our structure. This is still based on the in-place and the lifting cases. These are the exact same load cases and load combinations that we used for our structural code checking, except now we're checking the entire structure using finite element mesh. This allows things such as going in and looking at hotspots. So maybe, for example, I would need a stiffener here on this white flange. Or maybe I could reinforce where the jumpers are. The stresses seem kind of high here. So this is the in-place. And if I switch over to the lifting analysis, here I was only interested in the pad eye and to check my pipe to make sure that I have enough weld thickness here on my pad eye, enough length on my pad eye to transform the sling load, which is shown in yellow, into my pipe. This was all done using finite element, so I did not have to do any hand calculations or using spreadsheets. And the stresses are listed here. The contour of the stresses is listed on the right side here. So this is the kind of control that you have using Sesam, and it's really one of the big advantages of using Sesam is that you can go from structural code checks into a finite element mesh. This is using the same software. I did not have to resort to any second software to perform any particular purpose. I strongly believe that Sesam is a total solution, especially when it comes to subsea equipment. The next step is looking at a simulated lift through the splash zone. So the purpose of that is to get the correct dynamic amplification factors, to get more accurate and less conservative dynamic amplification factors. And that is using the same model. So I'll see you in SEMA. Hi, so now we're inside SEMA. This is one of my favorite new toys. The purpose of this model was to simulate the lift through the splash zone to get a time history of the forces on the slings, to get a more accurate, less conservative dynamic amplification factor, because the ones we were getting from installation contractors were extremely conservative. So this was a way to facilitate the communication between the engineering firms and the installation contractors. So in this model here, we represented three phases. The first one is a lift through the splash zone. As you can see, it's being lifted with the mud mat, which is not typical, but was just for this example. The first phase is the actual lift through the splash zone. And one of the outputs is going to be a time history of the forces on the members and in the slings. The second phase is the manifold standing still in the water column with the heave of the waves going up and down. And finally, the third phase is the lift up from after 30 years, that they will have to lift it back up, so that was also represented. And we were trying to find the maximum sling load so we can get the best dynamic amplification factor. So next is going to be taking this model and applying some nonlinear accidental limit states on the structure. So we'll be doing some ROV impact and some dropped object analysis. I will see you next. And here we are. This is our nonlinear silver USFOS, and the purpose of this model was to simulate an ROV impact on the structure, which is one of the code requirements when designing subsea equipment. And this is the same model that we used for the in-place lift and transportation. It was just converted over into this module. It's nice and easy. There's no complications there. We also simulated the ROV impact, and I will show you the results. This structure was modeled on soil. That is why you see some sort of jiggling there, but that is normal. And you can see here the permanent deformation when the ROV impacts. This is one of the, again, when the total solution of Sesam is I can simulate this using the same suite of software. I did not have to go to different software to provide me with this tool. This is, to me, very impressive. Next will be a dropped object analysis on a panel that is on the structure up here. And here we are. This is the dropped object analysis on the panel. This panel is located on the top of the manifold that we saw earlier. The purpose of this model was to check the panel to see if it can take the code requirement of a dropped object. And this was modeled in Genie and then imported directly into USFOS. It was a seamless conversion. And these are the results. USFOS is a great tool. It allows you to go in and check the energy of the system. It allows you to see what the deformation and the maximum deformation in the system is. Allows you to go in and find the stresses in an element, and has this great tool for doing anything that is nonlinear. Next, we will be doing an installation analysis on the manifold. The case was the manifold was being installed on uneven ground, so we had to simulate that. Finally, this is the installation analysis. As was mentioned earlier, the case was this manifold was being installed on uneven ground. I simulated the contours of the seabed by adjusting the stiffness of these nonlinear springs at the bottom. And this was also modeled in Genie and then converted into USFOS. And these are the results. I'll slow it down a bit here. So at the point of impact, it should impact here first. There you go. So it impacts here because the seabed is at a higher elevation here than on the back there. So first initial impact and then the follow-up impact. And then it permanently comes to rest, and you can see there's some stresses inherent in the beam due to that deformation. This concludes this video. I hope you enjoyed it. The purpose of this video was to give you a brief overview of how to design subsea equipment, in this case a manifold, using Sesam.